starting my 8 minutes now. The Sam's here. Ready, set, go. Okay, so our indie lab, I did it with Elise Freeman in second hour, but she's doing robotics right now. So our indie lab is called Dunder Mifflin Inc., a paper company, and indie lab, because it's about paper. So the purpose of our lab was to figure out the physics of paper folding, basically. It started out pretty abstract, and then we obviously got more focused. So we tested lots of different things and took lots of different data. We had 7 different types of paper, and we used different mass, different amounts of mass to get them to fold, and different amounts of time. And we measured the angle so that the paper folded, which I'll describe later in the procedure. Our hypothesis was that we would be able to estimate the amount of time that it would take in order to get a piece of paper to fold completely to 0 degrees. We didn't estimate what that time was, we just thought we could find it. Okay, so our papers were Christmas paper, construction paper, index cards, newspaper, notebook paper, poster board, printer paper. Yeah, poster board. Anyways, Christmas paper, we got it Office Depot or Office Max or something. It's just it's a little bit thicker than normal printer paper, and it was green. If you want to see the paper, I have it all here. I can show you guys after, but I don't see why you would really want to see it that much. Anyways, and then we used the cart masses and a protractor to measure the angle. We used meter stick to measure, because we measured the surface area of the sheets so we could find density. We masked them with a triple beam balance, and we measured the thickness with a micrometer caliper. Those are the equations that we used. Pretty self-explanatory stuff. They're not difficult equations. Because we found the surface area of this sheet, and then the way that we found the volume of the sheet was I measured the length and width of each piece of paper, and then multiplied that by the thickness of the paper, which is kind of like length times width times depth. So yeah. Okay, so the first time we tried to take data, we didn't know how we could actually get it, and we had to start over a couple times. We had the piece of paper, when we were trying to measure the angle, we had gravity affecting it, because we would put the piece of paper down on the table after we take the masses off, and it would be this much folded, but then gravity would pull it down a little bit. So what we did was we took it and, so it was laying like this when we had the masses on it folded, and then we would take the masses off and it would kind of unfold, and we would set it up like this on the table so that we could measure the angle without gravity being an issue. And yeah. Okay, so we used different masses. We didn't use it, we used either 250 grams, 500 grams, or 750 grams, depending on the size of the paper, and because our sheets were, we don't want to use the same amount of mass for our big sheet of poster board as a little index card. So it was just based on what made the most sense. And we put that amount of mass on the paper, we would fold it, we would hold it, fold it like this, and then we put the mass on. And then we left it there for 3 minutes, 5 minutes, and 10 minutes on different sheets. And then we measure the angle. Yeah. Our data table was really, really tall and wide. So this is just one sheet. So this is all of the data we took for just the Christmas paper. So we took it for 3 minutes, 5 minutes, 10 minutes. And we measured all of those lovely things. Yeah. Really great presentation. Okay, graphs. Okay, so these are the graphs that weren't very pretty. So this one, can I step over here?
Sure.
So we measured the area ratio. So the area of the cart masses over the surface area of the sheet of paper was that area ratio over the angle with the mass on. So when the paper had the masses on it, how folded was it? And there wasn't really a correlation. It didn't really. I mean, I guess you could kind of say go like this, but we didn't really think there was a good correlation there. This one. So later on, you'll see a prettier version of this graph. We made 2. This is that same angle with the mass on versus the density of the paper, and this is for 3 pieces of paper that had the same mass on them, 250 grams. But these angles are 3 degrees, 5 degrees, and 4 degrees. So the reason that they're probably not the shape that the other one is because those are really small angles and really hard to get the actual angle about. One more ugly one. Oh, there's a lot of these graphs, which is, so this is after we took the masses off and we measured how folded it was versus time. Like there's just the 3 different trials for 3, 5, and 10 minutes. This is for poster board. It just didn't look the way the rest of them did, and we think it's because we had a hard time with the poster board because it was so, like, it was a big sheet, and so we probably just took bad data. Okay, so here's the other graph. So this is the same graph, angle with mass on versus density of paper for the 3 types of paper that had 500 grams on them, and it made a really pretty, like, like a little upward curve there, which I think the other one probably should have, but didn't because the angles were so small. Then this graph is what we have a lot of, which is angle with mass removed. This is what the poster board graph should have looked like, which is a nice little decaying exponential there. So it makes sense because each degree of folding should take longer. Like it takes longer to get it more folded the more you're trying to fold it. And according to this graph and the other ones on the next slide, it should take theoretically infinity to get them to fold to 0 because it looks like it's asymptotically approaching 0. And then here are a bunch more of those graphs. They're all going like this, and this is all of the sheets of paper, angle of mass removed versus time. So sources of error, it was really hard to get the paper to crease. Like we thought that we would get like a definitive crease in all of our sheets of paper, and we really didn't. Like none of our angles were any bigger than or any smaller than 50 degrees. So they didn't get it nearly as creased as we thought they would. Micrometer calipers took forever to figure out how to read. And it was kind of hard to balance the paper, or to mass the paper on a triple beam balance. And the timing, we tried to take errors data all together. So we were timing 3 minutes, 5 minutes, another 3 minutes, all at the same time. So we could have been off a little bit on that. So, in conclusion, I have 47 seconds left. Shoot. I said all those things already.
Can you read it?
Thank you. I can say all those things already.
Why are you clapping for yourself?
Huh? Yeah, because I did an awesome job, Robbie. Does anyone have any questions? Rashawn?
So you said that you turned the paper sideways to measure the angle to get rid of effects of gravity. Did you do you think that friction played a role in your in error or something? You know, friction between the paper and the table.
It might have. We tried to hold the paper up and see. Maintenance are up. We tried to hold the paper up and see where it would naturally fall, and then put it down, just just so we could measure the angle. But it could have if it wanted to move out, maybe it didn't because of the friction. Mick?
Did you measure how close you put the mass to where you were creasing it? Do you think that made a difference?
Yeah. For each of them, we did so. Can I draw on the chalkboard?
Yeah.
So, if you have the piece of paper like this, right, and when you fold it, and then that's from the side, but if you look at it from the top, it looks like this, a half sheet of paper. We put, depending on how many masses there were, we just put them like this, so that this is the crease right here. All of them were, this part was in line with the crease. So, for the index card, they kind of hung off the side a little bit, but the poster board, they, didn't. So, we tried to keep it in the same space, though. Yes, Dr. Schuster.
Did you find any relaxing back to flat? I was kind of going off of Rashawn's question. When you found the natural after it had been creased and you shook it a little bit, found the natural, did you find that if you would wait a minute that it would go back, remember what it had?
Yeah, it especially did that with the when we didn't affect for gravity because it would fall down. Because what we would do is we would lay the paper flat and then see if it would do this, which it's hard to do that when you're going against gravity. But when we were doing lots of trials at once, if we would look at our pile of paper that used to be folded, it would unfold. Not completely, but it would not be super folded anymore.
I wonder if you get the same graphs, time dependence of unfolding, you know?
Maybe. That'd be cool. I think there's another slide. Yeah, forgot about that one. There's one more after this too. This is not where there were supposed to be questions. Anyways. Oh, and then we thought it'd be really cool if we could find a folding constant, like
Yeah,
a physical property of different types of paper that would indicate something about its foldability, which would be super cool. But we didn't do that, but that would be cool.
Like the density of the paper?
Yeah, but I don't know.
The material it's made of.
Yeah, I don't know. It would have to relate to like all kinds of things. I don't know. But that would be super cool. Okay. That's it.